Hi, in a previous video I did a teardown of this St. Jude medical House Call Plus transmitter. It's designed to connect up to your pacemaker and extract the data from it and send it back via the phone line. Well, this particular model, the House Call Plus transmitter, has an ECG function as well, and we took a look at some of the circuitry last time, and well, some people wanted me to play with this, so okay, let's see if we can actually get some ECG data out of this. Normally it's just they've got a separate isolated thing, goes across the transformer into the ADC here into the DSP, and then it's, I presume like a snapshot of that is sent back, or maybe even live data sent back to the medical center or your doctor or whatever it is. I think it's a service online you subscribe to, and then your doctor can access it and all that sort of stuff. But anyway, I thought it'd be interesting to see if we can actually get some ECG data out of this, because these can actually go quite cheaply. I've seen there's one currently on eBay for like 26 bucks, buy it now or something. So it could be a really good way to get like an experimental ECG system, because it's nice and safe. As I pointed out in the previous video, not only do we have a medical grade power supply with it, and yes, I will do a separate teardown of that medical grade plug pack in it, but we've got a medical grade isolation transformer in here. We've got all the ground separation. We've got the high value high voltage resistors in here in series with it, in series with each of these leads, and and the ground isolation. So pretty much, even if there's a lightning strike or something, you're not going to die if you've got these hooked up to both of your wrists. So it's pretty darn safe way to experiment. So let's probe around and see if we can extract data out of this, because all this circuitry around here is just the analog stuff. It's just going to be an ECG amplifier, a difference amplifier, and then sending that buffer and sending it over the transformer to the ADC over here. Alright, so let's have a look at some of the circuitry here, and as I said, this is all the isolated side. You can see the big safety isolation here, and also going under the two big power resistors there. And of course these aren't power resistors because they're dissipating a huge amount of power. They're 330k a pop here. They're used because they're high voltage resistors, so that's what they're being used for. So all the big safety isolation here. So all these grounds are completely separated. Now we've got ourselves an Opto Coupler here, the Vishay CNY64, and if you go look at the data sheet for that thing, then this side over here, these two pins are the LED, and this side is the photo transistor. So it's sending data back in that direction. So it's sending something from over in all this analog stuff. These are all just op amps and comparators and stuff like that. So this is purely just an analog amplifier for the ECG signal, which is picked up over here. So it's obviously sending something back, so we don't have to worry, although we might want to probe off that to actually see what's coming out of it. But really what we want out of this thing, of course, is an ECG signal to see if I can get my heartbeat out of the thing. So anyway, there's data coming back across the transformer like this, and obviously they're powering over the transformer as well, so they've got to be transferring that power over. I don't see how else they're doing it. Something has to be powering all these. Anyway, we should be able to pick data off here. And now this is the ADC chip, sorry, that's the ADC chip there, and that's our DSP processor. And we don't really want to read the digital data out of this ADC. That's just silly. So what we want to do is probe the analog signal, and look, there's a test point there, TP5. Look at that. That's handy. And there's also other test points on this side here, and well, they could be power supply test points, but more likely they're actually signal test points. Anyway, worth checking out to see if we can actually tap off the signal from one of these test points. So we don't even have to, maybe if we're lucky, don't even have to go in and reverse engineer any of the circuitry to find out where the signal path is and actually probe the thing. You don't want to be probing over here, by the way. This is all going to be the differential amplifier. You want to probe at the final driving point. The ECG signal should already be scaled up by all this circuitry and maybe level shifted or whatever on the ADC here, so that it inputs the right signal level, so you maximize your 10-bit dynamic range of your ADC there. So let's have a probe around. Now, first things first, we want to find a ground point on this thing. And usually these PCB mount studs here aren't a bad way to do it. And they're, you know, well worth doing. But check out here. Here's a test point which says to ground. So there might be separate grounds here. So I'm just going to check these. I'm going to just make sure that these are grounded. And yep, so that stud there is grounded. And if we go all the way up here and probe these other ones, we can see that, yep, they're also, because you can see that the ground is continuous. You see that dark green under the board means it's all sharing a common ground. So, you know, wait, hello? That mounting pad there is connected to this ground over here, but this one is not. That is bizarre. And they're on the same, look at that. They're on the same, looks like they're on the same ground plane. You can see all the dark green under there, but that one's not actually connected through. That's interesting. So why is that so? Well, it's a trap for young players. If you have a look here, I've actually got it switched on. There we go. The LED is on. And we're probing around at why it was switched on. Oops. So look, if we probe between these 2 points here, look at that. We get minus 85k. That is completely screwy. But if we disconnect, ta-da, look at that. We're grounded. So what we obviously had there is enough voltage differential there to completely screw up and confuse this meter. So just be careful when you probe around this sort of stuff. If you are probing, if you do a resistance checking like this, make sure you got it unpowered. Alright, the other thing I want to do is actually probe around to see if we got voltage on this side of the transfer or the isolation here, so to power all this sort of stuff. So we've got ourselves a big ass tantalum cap there, so it's obvious that we're going to probe across that, and hello, we got 0 volts. We got nothing across that cap. Cap next to it, 0. Another tantalum over here, 0. What's going on? Power's onto the unit. I've got the LED on, but we're getting nothing across these caps. There's no power. It's almost as if there's no power coming across here at all to power this stuff. Huh? Alright, so let's start probing around to see what we get here. We have established that that ground point, it's got a little wire connecting to the crystal there, so we can conveniently hook onto there. Otherwise we could have like soldered a wire onto one of the those mounting posts or something like that. So that's a convenient place to put a ground point. And let's measure a few things. Let's measure our power supply first. We're 1 volt per division. There we go. So where it looks like we're you know, 1.8 volts there or something. That's probably the supply for the DSP perhaps. Let's go over to this other tantalum over here, 1 volt per division. There we go, 3.3 volts. So yep, that's all right. That's our typical 3.3 volt rail. Yeah, 3.3, everybody happy. So all the power on this side is good. Now, of course, if you keep your ground probe on this side of the transformer and then probe the other side over here, there is no ground reference on this point. So watch what happens. We're just going to pick up a whole bunch of 50 hertz crap. Is it? Yeah, there we go. Spot on 50 hertz. We're just picking up a whole bunch of 50 hertz crap because there is no longer any ground reference over there, and it doesn't matter what part of this circuit you probe over here. You're just going to pick up 50 hertz crap. It's useless. So, you know, just a little tip if you didn't already know, if you have got your ground reference point on the other side of an isolated transformer like this, you're not going to be able to measure anything on this side, so don't even try. And actually, if I wanted to probe on this isolated side, I haven't even found a good ground point for it yet. There's a mounting screw there, but it's not actually connected properly through. Yeah, I can see where one side of the capacitor here probably goes down to the internal ground plane in there, but you know, there's no convenient hookup point, and it looks like there's no ground test point like we got on these digital side over here. We've got a few ground test points over here conveniently, so yeah, you'd have to solder in something in there to do it. Anyway, I want to get this side first. Now if we measure on the side of the transformer here, I've actually measured one side of the transformer is connected through to the main ground here, and we're getting nothing basically on there. So there's, you know, there's no surprise that that's just, you know, 50 hertz crap. Don't worry about that. So yeah, we got nothing. There is nothing powering this side of the circuitry at all, and you've got to think, well, that's because that's under software control, and the thing hasn't connected, so it's realized, oh, I don't have to measure anything, I don't have to do that ECG stuff, because I'm probably not connected through to the phone line and established a connection, blah blah blah. So that is incredibly disappointing. So much for an easy, just be able to probe, you know, the output of the amplifier here and get an ECG signal on the scope. It's not going to be that easy at all. You know, it's possible. You can obviously coax it into doing it eventually, or you can hack into it to actually supply power to the circuitry and reverse engineer it, and, you know, figure out and just, you know, eliminate all this other stuff, like tear out the transformer and just, you know, wire in some power and onto here and just, you know, get the output of the final stage amp, and Bob's your uncle. But geez, very disappointed. And we're definitely getting no voltage on this side of the transformer here. Nothing. There's no power on these chips at all. Okay, so what I've done here, because we're getting no power on this side at all, obviously the software is not driving this side, or there's getting no signal on this side, so there's no power over here. So what I've done is I've sucked out that little puppy, and we can actually see what's going on here, and it's pretty obvious that the output of the transformer here, by, you know, assuming that this side is the input over here, which it is, then the output here, I don't even have to look up those two parts. I know that they're diodes. Okay, so we're getting some rectification happening there to generate the power, and that's our main filter cap. So that's all that this thing is doing, is just powering the transformer to get, it's just an isolation transformer purely to get power over here. That means the signal data must be going back over the opto coupler here, because we've already established, if you look at the data sheet for this thing, then the LED is on this side and the photo transistor is on that side. So there you go. It's much easier now to simply go and apply power to here. We can have a look at the data sheet for these chips and try and figure out what the maximum voltage here, because we don't have any schematic or specs or anything like that. Figure out the maximum voltage is, whack a voltage across here, and then we can start then probing around here and see if we can get a signal out. So I'm just going to ignore all of the rest of the circuitry, not even going to bother to power it up anymore, because it's completely isolated. Look at that. And then we should be able to maybe at least get this powered up, get an ECG signal out of here somewhere. Before we do that, we have to find out which one of these pins is connected through to the ground plane, and it's pretty obvious. There's the positive of the cap there, so that's just going to be going through, that's going to be a diode going through, so I reckon this one here is connected through to the ground point, and the ground point's likely the negative side of that cap, and bingo, there it is. And you can go down, say, the negative side of this cap down here. Yep, and as I said, there's no ground test point, so we should actually solder in just a little loop on there so that we can attach our ground probe down to that. But that entire ground plane there, you can see down in there the via going right down in there. There it is. From the negative side, it's going nowhere except down to that ground plane down there. So yep, that one is definitely connected through. So that's our negative input, that's our positive input. Just look at the data sheets for these op amps. You know, if their maximum voltage, say they're a low voltage one, might be 6 volts, and you might just, you know, whack 5 volts on there, for example. And as it turns out, we've got nothing to worry about there. Look, we've got an LM317 voltage regulator here. There we go. So we can read those resistor values, figure out exactly what we've got there. But there you go. So it's going to do the regulation for us. Beauty. Alright, so I've soldered on myself a ground test point here and a couple of fly-in wires. I've got that going up to, well, I will have it connected to the bench power supply, and because this is a LM317, it's only got a LM317L low power version, it's only got a current limit of 100 milliamps, so it's a good idea just to set your current limit on your supply to an arbitrary value of also 100 milliamps. So I'm just going to start out at a low voltage, wind the wick up until we can see the LM317 regulate, because I haven't bothered to read the values on those resistors and actually know what this thing operates at, and then you would set it like at least 2 volts above that. So I've got the probes just across the output capacitor there. Let's wind the wick up and see if we get any regulation on the output. 1.6 volts. Keep winding up. Winding up. It's drawing 710 milliamps, 4.2 volts, 5.6 volts input. So 2.5 volts out. Now you've actually got to be careful here. It turns out this LM317 is not actually powering everything. It's powering, well, it's obviously powering something, but the chips themselves, if we have a look at this LM393 comparator, for example, dual comparator, there you go, it's 4.5 volts, so it's actually powered from the input directly, so it's nothing to do with the LM317 there. So I've got 5 volts going in, of course, and we're going to get, you know, half a volt drop on the diode, of course. So yeah, got to be careful there not to wind up the input wick too hard, because it turns out it actually bypassed that LM317 regulator there and went straight to these straight to the op amps and comparators. Now these LMV824 op amps on here, if you look at the data sheet for those, well, they're only low power devices. They're only up to 5.5 volts voltage range. So, you know, really, like 5 volts input is fine for this sort of thing. You definitely don't want to go over 5.5 or 6 because of the diode drop. Then you risk, well, you damage the op amps. So, yeah, I mean, even if you were down at like 3 volts or something, it's probably enough dynamic range. You know, these op amps can work down to a low voltage, so, you know, pretty much it's going to work. So, yeah, I reckon 5 volts in there is just perfectly fine and dandy. Now, in terms of safety, of course, because I'm going to put these... Oh, I've already touched them. There you go. If I was going to... Geez, no, I'm just fine, because A, we're only working at 5 volts from our isolated bench power supply, just like you used to for all your projects. There's nothing dangerous there at all, and yeah, we are connecting the ground reference in this circuit, but once again, it's just like powering a regular circuit. And we've got the 2 big ass 330k resistors in series there. We don't even need those for stuff that we're going to do here, so this is all completely safe. You can muck around, even beginners can muck around with this sort of stuff when you've only got like an isolated 5 volt supply. No problems at all. And here we go. Yes, I've got my wrist strap on. No, it doesn't matter that I'm wearing the watch. And let's probe a couple of the test points around here and see what we get, shall we? So now I've got it powered from my 5 volts. So let's get in here and give it a whirl. And of course, this is not the best way to get an ECG, of course. You're like right at the end of your arms like this. Is, you know, it's one of the worst ways to actually get it. They need to be like on your chest, proper chest sensors and things like that to do it properly, because you might get, you know, impulses and noise coming from your muscles and, you know, everything else. So you probably got to be in a relaxed state. Anyway, we just need to see. So I'm just going to probe a random test point here. As we saw before, I'm going to probe TP8. And hello? Hello? What do we got there? We got something. Alright, let me probe TP6. Oh, yeah. Hello, look at that. We definitely had something there, and all of a sudden it... Oh, it's all over the shop. It's all over the shop, but we're getting something. Ooh. Oh. Alright, this is rather unusual. Oops. Trap for young players. Look at this. TP8 that we had before. Watch. If I touch the anti-static mat. Look at that. So, yeah. Oops. Something's going on there. Okay, let's not touch the anesthetic mat, even though this is, yeah, people will go, oh yeah, the anesthetic mat is conductive. No, they're dissipative. So they're, you know, ridiculously high resistance. But it's obviously enough to pick up something. I mean, we're dealing with very low level signals here, so I'm not going to touch the bench at all, and let's have a look, see if we can AC couple that sucker. And yeah, I'm not sure what's going on there, but is that a cardiac pulse? No, I don't think so. No, we've got an oscillator there, which is fine and dandy. Test point 1, no, that's going to be, no, we're getting zippity doodah at the moment. Alright, so what I've done is I've got it up on a wooden frame isolated here, so none of the input circuitry is touching the ESD mat at all, and we're going to probe TP8 again. Hello, what do we got there? And there you go, that's exactly the same signal that I was probing before, but I don't have the wrist straps on anymore. So let me actually just touch them again. Here we go. Ta-da! So I'm now holding, I'm just holding them, I haven't put them on. But there you go, have we got something? Okay, what I'm probing now is actually the output to that opto coupler. Okay, so what's driving that lead on the opto coupler there, and you can see jitter on this signal, and if I'm not mistaken, this might actually change with my pulse rate. So I'm gonna jog here. I'm jogging on the spot, see if I can get my pulse rate up. Here I am. Oh, come on, it's hard to get my, I'm quite fit, it's hard to get my pulse rate up, I'm sorry. Hang on, lost my probe. I have a naturally low heart rate, by the way, but I don't know, I reckon if I get my heart rate up, I reckon there's more jitter there. And if I stand still again and relax, you can almost see it beating to my chest. If I was moving my arm there, sorry, I was putting my hand over my chest to... And I think it's jittering to my heartbeat. I think. That could be an illusion, but that's the impression I'm getting. Now back to this signal that we're getting on test point 8 here. It's a, well, not sure what happened there, but yeah, it's a complete furphy because, well, it's nothing like an ECG signal, and it's not even in the same ballpark. In fact, we're using the wrong measurement technique on the scope here, because we're talking, you know, heartbeat like once per second, you know, boom, 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 right? So obviously we need to get into our, let's go into our horizontal menu here. We need to get our time base, instead of putting it on your usual time base, you want it in roll mode like this. And this is what roll mode is actually good for. And there's nothing on this test point that I can see anyway, but if we move it over to another one, TP6, bingo. Look at that. Hang on, we've still got some crap on here. But boom, 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 boom. There we go, and that follows my heartbeat. So that's that TP6 test point down in there. It's the output of one of the quad op amps there, and I've checked some of the other outputs, and I can't really find anything. This is like the best sort of signal I can find that actually matches my cardiac pulse. So you can clearly see my pulse in there, and watch this. If I go like that, I can make it, see, I can make it do stuff because I'm just, you know, this is, as I said, this is not the best technique for doing this sort of thing. You're going to pick up all sorts of crap, but cardiac pulse is definitely in there. Right, and I should be able to prove that by closing my eyes and measuring my pulse, and I'll tap on the oscilloscope every time I feel my pulse. So, ready? Let's make sure I've got a good waveform there. Yep, see blip, blip. So, here we go. Is there any correlation there? There should be. And if I stop that and turn on the cursors here, you can see that we've got a delta of about 980 millihertz there, which of course is slightly faster than 1 hertz, so slightly higher than 60 beats per minute. Works out to around about 61 beats per minute there. That's much higher than my naturally resting heart rate because I'm working here and doing all sorts of jazz. So, you know, it's a little bit elevated. Anyway, let's take that as a baseline. I'll keep the same roll rate and time base, and we'll be able to see. Let's now do some exercise and see if we can increase it. Whoa, there we go. And here we go, I got a few jumps in there, and yeah, you can see it's now much quicker. And there you go, we've got a delta of 2.17 hertz there, which works out to about 130 beats per minute. And I'm back on regular time-based mode now, and unfortunately I can't turn averaging on at such a slow time base, and averaging doesn't work in roll mode either, but I can like change to high res mode, which does that boxcar roll in average, but still we can't really clean up that signal much, and we're not really going to be able to see that cardiac pulse, I'm afraid. Here we go, settle down. Yeah, we're, you know, it's kind of sort of there, but nah. And because I know some people will ask, no, it's not the scope ground in here. If I use something like my LaCroix differential probe here, it's just even noisier. I mean, a single point ground, because our power supply is floating, so a single point oscilloscope ground there is not going to do anything, but that's just picking up all sorts of crap, so that's no good at all. And yes, I've tried all sorts of things like my Australian safety boots here, you know, just to isolate myself from the floor and, you know, stuff like that. And, well, nothing's working. I'm not copping a break. You know, I can't seem to get like an ECG, an actual ECG waveform out of the thing, which is a bit of a bummer, but it probably needs some more work and stuff like that. We're, you know, really tricky business trying to probe this sort of thing. You've got to eliminate all sorts of you know, environmental stuff and test setup and probing issues and things like that from the equation. So that's not easy at all. You have to systematically go through and cater for those things. But anyway, I think I did get at least something out of that. See if there's any correlation between my tapping and the slight modulation on that waveform. Here we go. Make sure, yeah, everything's fine. Okay, here we go. Any correlation? So obviously what they're doing is, you know, squaring up this signal really early and getting some sort of, you know, modulation of a clock out of it and decoding it that way. And so I'm not even sure if this thing actually, you know, can record like an ECG signal as such. So yeah, I'm not entirely sure what's going on there, but I'm pretty sure I found that is modulating in time with my heartbeat. If I hold my hand there and you know, I can actually correlate it to what's going on that scope there. Anyway, it requires further investigation and decoding and stuff like that, but there you go. That was my first crack at that thing anyway. So that's all I've got time for today, unfortunately, for playing around with this thing, but I'll whack up this video anyway. I don't like leaving things around, you know, until I absolutely complete them, because I might not get around to playing with this thing again. But there you go. There's just a couple of little experiments. I was a bit disappointed I couldn't just get, you know, a single-ended ECG waveform out of this thing, although maybe that was unrealistic. But anyway, I think I've found a correlation there with that digital output. So yeah, maybe that's how it's actually doing it. It's probably squaring it up early, and you know, I don't know, you might have no chance of getting an ECG out of this particular circuitry here. So anyway, I hope you enjoyed that fun little playing around, and if you've got any ideas or suggestions, please leave it in the comments. Catch you next time.